In this video, we solve problem 9.R.114 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find the Maclaurin series for the function f of x equals natural log of x minus 3. But I also want to show you something. They were asking us not just to find the Maclaurin series for the function, but they were asking us to use a table of power series for elementary functions on this problem. So if we click on that and we look at this, we see that there is a power series for natural log of x listed as x minus 1 minus the quantity x minus 1 squared over 2 plus the quantity x minus 1 cubed over 3, and so on. And it looks like the nth term is negative 1 to the n minus 1 times x minus 1 to the n over n, and so on. And we're told that the interval of convergence for this is 0 to 2, including 2, but not including 0. So that's what we're told, and that's actually what they expect us to use in order to answer this question. So I'm showing you someone's assignment where they got the wrong answer here, and this is the answer that they want. Now I will show you how to find the answer that they want using this entry in the table, because that's what they're asking us to do. But this entry that they give you is actually not a power series. Or excuse me, it is a power series, but it's not a Maclaurin series. They asked you for the Maclaurin series for the function. So they're asking for this answer, but it's actually the wrong answer. So I think I'll show you how to get the answer that WebAssign wants, and then I'll also show you how to solve the problem that they posed, which was actually a good problem. It's a really good opportunity to practice finding the Maclaurin series for a function. But this answer that they're looking for is actually not it. Okay, so let's talk about how to find the answer that they're looking for. They say in the book, in that table, that natural log of x is equal to this. And so that is a series that can be written in this way. Notice that that denominator always has an n in it. We've got a 1, a 2, a 3, and then the nth term has an n in it. So we're starting with n equals 1 here, and we're going to infinity. And given that n starts at 1 and goes to infinity, this is the expression for the nth term. Now, if you're taking my class, hopefully you see this and you know that this is not a Maclaurin series. This is a Taylor series for y equals natural log of x, centered at x equals 1, not x equals 0. And it's a good thing that they're centering it at 1 and not 0, because natural log of x is not defined at 0. So when they say to find the Maclaurin series for the function, and then they ask you to do this, that's actually not going to work very well. We couldn't find, well, maybe we shouldn't try to even find the Maclaurin series for this function, because that would require us to center our answer at x equals 0, and natural log of negative 3 is undefined. It's not going to give us a real number. It actually gives us a complex number, but we're not interested in those complex numbers in this class. So let's talk about how to get the answer that they want. To get the answer that they want, all they want you to do is look at this expression for natural log of x, and then replace x with x minus 3. That's all they're looking for. So you leave this expression alone, you leave the denominator alone, and you replace x with x minus 3. And of course, x minus 3 minus 1 is x minus 4. So this is a Taylor series for this function, but it's not a Maclaurin series. That can be written this way. It's x minus 4 minus x minus 4 squared over 2 plus x minus 4 4 squared over 3 minus x minus 4 squared, or cubed, excuse me, in the wrong exponents. That should be a 2 and that's a 2. That should be a 3 and that's a 3. This should be x minus 4 to the 4th over 4, and so on. Oh, sorry, I was off the screen there. But this is actually the series that they are expecting you to enter. And so this is the answer that you would enter. But the problem is this is not a Taylor series or a Maclaurin series for this function. This is a Taylor series for this function. For y equals natural log of x minus 3, and it's centered at x equals 4. Now I was going to say, let's find the Maclaurin series of this function, the one that's centered at 0, but that's actually not going to work because natural log of x minus 3 looks like this. It's actually just like the natural log of x function, but it's shifted over 3 units to the right. So it has an asymptote at x equals 3. When x is 4, it equals 1. And it roughly looks like this. We're going to have a really hard time finding Maclaurin series for this function because it's not even well defined at x equals 0. If we wanted to, though, we could find the Maclaurin series for natural log of 3 minus x. That's one that is well defined at x equals 0. So let's do that instead. We've actually already answered the question that, or we've answered in the way that WebAssign was expecting us to answer. But we are not able to answer the question that they asked because this function is not well defined at x equals 0. So I'm just going to call this N.R.114 star. So this is a modified version. Let's find the Maclaurin series. For natural log of 3 minus x. This function is well defined at x equals 0. So when x equals 0, we get natural log of 3. Now, if you wanted to, you could write this way. This is natural log of, if I factor out a -1 times x minus 3. So this is well defined as long as x is less than or equal to 3. And we can think of this as 2 different transformations on y equals natural log of x. When I replace x with an x minus 3, that shifts everything over 3 units to the right. And then when I multiply this by -1, it flips it. And now when I'm thinking through the order of operations, I think we need to do this on the outside first, the reflection first, and then shift by 3. So this is, the graph should be the graph of y equals natural log of x reflected. If I replace x with -x, that's going to reflect across the y-axis. And then we want to shift 3 units to the right. So here when x equals 2, natural log of 3 minus 2 would be natural log of 1, which is 0. So what we would see is a graph that looks like this. It still has an asymptote at x equals 3. But because I replaced that x minus 3 with a -1 times x minus 3, instead of being defined over here, I made it defined on this side. So it's reflected. And when x is equal to 0, we would get natural log of 3, and I'm not even sure what natural log of 3 is. Well, natural log of 2.7-ish, natural log of e would be 1 because e to the first power is 1. So it's a little bit more than 1. So I'll just draw my graph that way. Okay. Now this is a function that is well defined at 0, so we can actually find the Maclaurin series for this. Let's practice that. Now remember, when you're finding the Maclaurin series for a function, it's going to be the sum as n goes from 0 to infinity of the nth derivative of the function evaluated at 0, all divided by n factorial, times x minus 0 to the nth power. Or in other words, this is f of 0 plus f prime of 0 times x minus 0 to the first, plus 1 over 2 factorial, which is just 2, times f double prime at 0 times x minus 0 squared, plus 1 over 3 factorial times f triple prime at 0 times x minus 0 cubed, and so on. And we keep going, and I'm sorry that x cubed got sort of cut off at the end of the page. But the idea is this. Everything here is well known except for this pattern for the nth derivative of the function at 0. If we can find that, then we can find the Maclaurin series for this function. So let's do that. We've got f of x equals natural log of x minus 3, or 3 minus x, sorry. And f prime of x is equal to, well, the derivative of natural log is 1 over the inside function times the derivative of the inside by the chain rule. So it's negative 1 over this, or I could just take that negative 1 and multiply in the denominator instead. So I could think of it that way, but it'd probably be easier or better for us to think of it as negative 1 times this and a positive 1 in the numerator. Negative 1 times 3 is going to be negative 3. Negative 1 times negative x is going to be a positive x. So we can think of f prime as x minus 3 to the negative 1. And then we'll compute the next derivative. Well, because we flipped the order by distributing that negative 1 in the denominator here, that when we use the chain rule, the derivative of the inside is just going to be 1 every time. So this is going to be nice and easy. For the second derivative, we'll get negative x minus 3 to the negative 2, because we're bringing the power down. We're multiplying by this expression to the 1 less power, times the derivative of the inside, which is 1. And we keep going. And I'm going to leave it factored because I'm looking for a pattern. So then I'll have the third derivative is negative 2 times x minus 3 to the negative 3 times the derivative of the inside, which is 1. And I'm multiplying by the derivative of the inside due to the chain rule. Take the derivative again. We're going to have negative 1 times negative 2 times negative 3. So we're bringing the power down. Multiplying by our expression to the 1 less power, and so on. And then we're looking for a pattern for the nth derivative evaluated at x. Well, I notice that this starts off positive, and then it's negative, and then it's positive because a negative times a negative is a positive. And then we've got a negative times a negative times a negative, which is negative. So it's positive, negative, positive, negative. So this is going to involve an alternating expression. Notice that it's positive when we have the first derivative, and it's negative when we have a second derivative. So I need this expression to either be negative 1 to the n or negative 1 to the n plus 1. And I'm trying to decide between the two of those by thinking about whether I need the expression to be positive or negative when n is odd or even. I need it to be even because I want negative 1 to an even power is positive 1 when n is odd, and I need this to be odd when n is even because you're going to have negative 1 to an odd power when n is even. So I think we need an n plus 1 there. Let's check it out. When n is equal to 1, I've got negative 1 to the 1 plus 1, which is negative 1 squared, which is positive 1, so we're good. When n is equal to 2, I have negative 1 to the 2 plus 1, so negative 1 cubed, which is 3 negative 1s multiplying each other, which is obviously negative. So this is going to give me the right sign. What else do we notice? Well, they all have an x minus 3. And they've got a negative power there. Sorry, I dropped my pen. I had to pick it up. Okay, now I'm looking for a relationship between that power and the order of the derivative. This is a -1 when that's a first derivative. That's a -2 when that's a second derivative, a -3 when we have a third derivative, a -4 when we have a fourth derivative. So the order of the derivative is the same as that number that's multiplying the -1. So if this is the nth derivative, this must be a -n. Okay, cool. And then out front, we also have this sort of factorial thing happening. When I've got a 4 here, I see a 1 times 2 times 3. So that's a 3 factorial. When I have a 3 there, I've got a 1 times 2. So that's a 2 factorial. For a 2, I've got a 1 factorial. You might say there's no factorial there. Well, you can think of that as a 0 factorial. So when n is equal to 1, we have a 0 factorial. When n is equal to 2, we have a 1 factorial. When n is equal to 3, we've got a 2 factorial. When n is equal to 4, we've got a 3 factorial. So we have a factorial, but if this is n, this is 1 less than n. So we'll have n minus 1 factorial there. And I think that takes care of it. We took care of the signs, we took care of the factorial factor out front, and then we took care of the x minus 3 to the -n. Okay, now if we want the Maclaurin series though, we never want to substitute in a function of x here. The x's are taken care of by that x to the n. This is just supposed to be a number. That's a value of the nth derivative at x equals 0. So we've got to plug in x equals 0 to this expression. Oh, and notice one other thing. This pattern holds for n equals 1, 2, 3, and 4, but it doesn't hold for that 0th derivative. For the 0th derivative, it doesn't look anything like that. It's going to be a natural log of 3 minus x. So this is the nth derivative of f evaluated at x for n equals 1, 2, 3, all of those positive integer values. N equals 0 has to be handled separately. Okay, so now we will take this and we'll evaluate at x equals 0. And then simplify. So we've got -1 to the n plus 1. This is a -3 to the -n times n minus 1 factorial. And we could simplify that a little bit. I could make that a -3 to the n in the denominator because of our exponent properties. X to a negative power is 1 over x to the same power but positive. So I can just put that in the denominator. And I see this -1 to the n plus 1 and a -3 to the n. And I'm thinking I'd like to simplify that if I can, and I think we can. So I will simplify this guy using this property. Remember, if you've got 2 power functions, you add the exponents. That's true whether the base is a variable or not. So if I have x to the -1, or -1 to the n plus 1, excuse me, we're going to have -1 to the n times -1 to the first times n minus 1 factorial. And then down here, I can think of that as a product of -1 and 3. If you've got a times b to the n, well, you can apply that exponent to both of those guys. So you'll have -1 to the n times 3 to the n, and the -1 to the n's reduce. And so we've got this expression. So natural log of 3 minus x can be written this way. It's the sum as n goes from 0 to infinity of the nth derivative of f evaluated at 0 over n factorial times x to the n. And that's f of 0 plus the first derivative at 0 times x plus the second derivative at 0 over 2 factorial times x squared plus the third derivative at 0 over 3 factorial, which is 6 times x cubed. And we keep going. We keep going indefinitely. But this, we have a pattern for. We've got an expression for the nth derivative of our function evaluated at 0 for n equals 1, 2, 3, and so on. So this part here can be written just at once with an infinite series. Well, the sum as n goes from not 0, but 1 to infinity of the nth derivative of f at 0 times x to the n over n factorial. We just took out the n equals 0 term right there because for the n equals 0 term, that doesn't match that pattern. So we'll just have f of 0 here. Our function f is natural log of 3 minus x. So this is going to be natural log of 3. And then we're adding the sum as n goes from 1 to infinity of this nth derivative of f at 0, which was this expression here, all divided by n factorial times x to the n. And the nth derivative at 0 was a -1 times n minus 1 factorial over 3 to the n. And that negative we could factor out if we wanted to. I think I will. And this n minus 1 factorial and the n factorial can be simplified. Anytime I've got two factorials, a quotient of factorials, I can always write the one that has the larger number here in terms of the smaller one. Since n is larger than n minus 1, I can write this way. This is 3 to the n times 1 less than n, that's n minus 1. And then times everything after that, all of the different positive integers all the way down to 1. So this n factorial can be written as n times n minus 1 factorial. Now, if you're not sure about that, you might just check out like 5 factorial over 6 factorial. Got 5 times 4 times 3 times 2 times 1. It's always good to just plug in values of n and then see if you can't just recognize the pattern with some numbers and then think about how that would generalize for n. We'll see the 5 factorial is there, and we're just left with the 6. Same thing is true if we had 4 factorial over 5 factorial, with 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. See how all those reduce and we just get the 5. In the same way, if I've got an n factorial down here, this is n times 1 less than that. 1 less than 5 is 4 times the rest, right? All the way down to 1. Well, that is that factorial. So we can think of this 4 factorial over 5 factorial as 4 factorial over 5 times 4 factorial, and those reduce and we get the 5. In the same way, we've got an n minus 1 factorial here and an n minus 1 factorial there, and we get that. And so we can write our Maclaurin series for this function this way. I'll have an x to the n in the numerator, a 3 to the n, and an n in the denominator. And we're taking the sum as n goes from from 1 to infinity. And we do have to worry about convergence issues. We should say, when does this actually converge? In order to figure out where this series converges, I guess we could use the ratio test. I think I will do that. Let's do the ratio test for that. This is part of an exam review. So even if it's not the answer that WebAssign wants, it's still good for us to practice this because we're getting ready, for an exam. So I've got natural log of 3 minus x. Turns out to be this, or this happens to be its Taylor series. We haven't proved convergence yet. So I'm just going to put a little question mark there. This is the Taylor series, or the Maclaurin series, generated by this function. And my question was, okay, when does this series converge to this function? Well, when does the series converge in general? Let's just say that. I don't think I'm going to prove that this series converges to this function in this video, because that's not as important for the exam, but you should be able to tell whether this series converges or when that series converges using the ratio test. That is very much fair game for your exam. When does the series converge, not converges? There we go. So I'm just going to focus on this because we're just taking this and then we're adding a constant, multiplying it by -1 and then adding a constant. So this expression will converge when the series converges. In order to figure that out, I will use the ratio test, where this is my a sub n. So we'll take the limit as n goes to infinity of a sub n plus 1 over a sub n in absolute value. And a sub n plus 1 looks just like this, but you replace all the n's with n plus 1s. And then we're dividing by a sub n. So we're just going to take a sub n, flip it, and multiply. And then because multiplication is commutative, we can sort of change the order of things as long as the expressions in the numerator and denominator remain equal. So I'm going to regroup. I'll group the x to the n plus 1 and the x to the n together. And I'll write that x to the n plus 1 as x to the n times x to the first. So we've got that property from algebra that allows us to say that if I'm multiplying these guys together, I add the exponents. That works backwards as well. And then I want to do the same with the 3 to the n and the 3 to the n plus 1. Those are positive, so I'll just leave those alone. That's in the numerator and that's in the denominator. And then I'll group the polynomial expressions. I've got an n up here and an n plus 1 down here. And if you're saying, how is that equal to that? Just multiply. This times this times this is the same as that times that times that. I actually kept the numerator in the same order. In the denominator, I changed the order. I claim that this times this times this is the same as this times this times this. And it is, because we can multiply in any order we want. I'm talking about real numbers, and multiplication is commutative with the real numbers. Okay, so the x to the n's reduce, the 3 to the n's reduce. I've got an infinity over infinity indeterminate form. Whenever you have that with polynomials, we always divide by the highest, power of n in the denominator. And so what we get here is the limit as n goes to infinity of the absolute value of x times 1 over 3 times 1 over 1 plus 1 over n. And as n goes to infinity, this guy approaches 0, and we end up with this expression. Absolute value of x over 3 is our limit. Now remember what the ratio test says. The ratio test says that this series that we started with is guaranteed to converge when L is less than 1. So that's just saying that the absolute value of x over 3 is less than 1. So the absolute value of x is less than 3, which means that x is between -3 and 3. And then if L is greater than 1, and that would happen outside this interval from -3 to 3, L is going to be greater than 1 when x is less than -3, or when x is greater than +3. The series is guaranteed to diverge, but we're not sure what's going to happen at the endpoints. There's a sort of a question mark there, because our ratio test is inconclusive at these endpoints. And if you're saying, what do you mean? Why is it inconclusive at the endpoints? The endpoints are the x values where L would be equal to 1. Absolute value of x over 3 is equal to 1 when the absolute value of x is equal to 3, which means that x is equal to -3 or 3. So the test is inconclusive at the endpoints because the test is inconclusive when the limit equals 1. So if we want to figure out what happens at the endpoints, we have to substitute the endpoints into this expression. So let's test that expression when x is equal to 3. The sum as n goes from 1 to infinity of x to the n over 3 to the n times n. And we're replacing x with 3. That's convenient. Those guys reduce. And we just get this harmonic series. That's a p series with p equals 1. P equals 1 is clearly less than or equal to 1. So the series diverges. It's a divergent p series. And then at x equals -3, we have the sum as n goes from 1 to infinity of x to the n over 3 to the n times n. We're replacing x with -3. So you can replace that -3 to the n in the numerator with -1 to the n times 3 to the n over 3 to the n times n. And those guys reduce, and we have an alternating harmonic series. I'm not going to prove it here, but this one converges by the alternating series test. And it's actually pretty easy to prove. B sub n is just 1 over n. And clearly B sub n approaches 0 as n goes to infinity, and B sub n plus 1 is definitely less than or equal to B sub n for all n, for which this series is well defined. So this converges by the alternating series test. So our series converges on the interval from -3 to 3, including -3, but not including +3. Whoops, I got that backwards. There we go. So the interval of convergence is -3, which is included, to 3. 3 is not included, and the radius of convergence is half the length of that interval, which is 3. Okay, so that was a good review. But the answer that Webestein was looking for on that homework problem, actually, it's not a very well-posed problem after all. We can't find a Maclaurin series for this function because natural log of -3 is a complex number and we're only interested in real numbers. What they were looking for you to do was to use this from their table of power series and then just replace x with x minus 3. And then we get this Taylor series for natural log of x minus 3, but it's not centered at 0, so it's not a Maclaurin series. It's actually centered at x equals 4. In order to come up with a problem that we could center at 0, I had to change that x minus 3 to a 3 minus x, because this function is well defined at 0, and we were able to come up with a Maclaurin series for that using this process where we're just trying to find a pattern for the nth derivative evaluated at 0. And then after we did all that, we said f of 0 doesn't match the pattern, but everything else works out fine. We have this, and we asked ourselves, okay, well, when does this series converge? And we used the ratio test, and we tested the endpoints to find both the interval and radius of convergence. Now, we did not prove that this equals this. That would have to be done another day and another way, but you're not going to be asked to prove anything like this on the exam, so we're going to skip that, at least for this semester. But I think that's a great question, maybe for a future semester, or maybe for extra credit.